Section 4.5 is about the intermediate value theorem, which should be a theorem that is familiar to you from calculus. You were probably taught how to use this theorem, but you probably did not actually prove that this theorem was true, and that's what we're going to do in this section. So first of all, I have an awesome joke here that I couldn't resist sharing. So why did the chicken cross the road? The answer is the intermediate value theorem, because he was standing right here and then he ended up here and he walked there continuously, and the only way to do that is to cross that line, otherwise you would have a jump discontinuity. All right, so just some facts that I want to highlight. We've talked about whether or not sets with certain topological properties for their for the domain of a function, whether or not that means that when you plug them into a continuous function, does the range or the image set have to have that same topological property. And so far we've seen that the continuous image of a compact set is compact. So that's another way of saying if your domain is compact and your function is continuous, then f of the domain is also compact. That's the theorem that we call the preservation of compactness. The second fact that I have here is a result of the intermediate value theorem. The intermediate value theorem, high level, simply says that the continuous image of an interval is, again, an interval. So if you start with an interval, you plug it into a continuous function, the range that you get out should also be an interval. So here's the formal statement of the IVT. It says, suppose you have a function defined on the interval a to b, and you know that it's continuous. Then any L value between f of a and f of b, so you can think of any L is like a value of y on your graph. For any number that sits on the y-axis between f of a and f of b, so maybe it's here, and by between I mean it's not actually equal to f of a or to f of b, it's just a strict inequality. And it could be that f of b is the larger number than f of a. I'm just showing one example. For any number that you pick, there has to be a place where the function achieves that value. So what you can do is you can take a line at y equals L, and what you should see is that that line has to intersect your curve at least one point, C. So writing that up, the curve or the line y equals L must intersect y equals f of x at least one value C in my interval AB. And this is whenever L is between f of A and f of B. So I could pick any number I want on the y-axis that's between f of A and f of B. I could have, for example, put my L value right here. Maybe this is y equals L prime. Notice in this case that I actually intersect at 3 different C values. The IVT just says we're guaranteed existence. It doesn't tell you what the values are, and it doesn't tell you how many values there are where you intersect. It just says that there has to be at least one intersection, and that's no matter what line I draw and what horizontal line I draw between f of A and f of B. So high level, IVT is really that it's the theorem that is telling us that you can't draw the graph or to draw the graph of a continuous function, you would do it without picking up your pencil. meaning you're not going to jump over any of the y values as you traverse the curve. To prove the intermediate value theorem, we're actually going to prove the special case where L is 0. Then if I wanted to say that the IVT also had to work for L being a non-zero number, it would just be a shift of our argument. So what I mean by this is I'm going to assume that my function values that want, like f of a is, for example, a negative number, and that f of b is a positive number, and I'm going to show that my graph has to cross the x-axis somewhere. So let me write this down. So we will prove the special case where L equals 0. So in other words, I'm going to say, i.e., if f is continuous, on AB without loss of generality, I'm going to assume that f of a is the negative number and that f of b is the positive number. So 0 here is playing the role of L. It's the number between f of a and f of b. Then there exists a C in AB such that f of c equals 0. So I'm thinking of this as a function where if this is my a value, f of a is going to be down here. It's going to be negative. And if this is my b value over here, f of b should be positive. And I want to prove that there has to be some place where I cross the x-axis. So I'm trying to say that I have a c value right here where f of c is 0. So the proof that I'm going to offer for this is going to be a little bit different than the proof of what's given in the textbook. So the textbook actually proves this theorem called the preservation of connectedness. And remember, we skipped section 3.4, which was talking about connected sets. We said that a connected set on the real line is really just an interval. So because we don't have that result to make reference to, I'm going to show you how we can prove this claim just using supremums and our understanding of the axiom of completeness. So there's going to be some upfront things that I need to tell you that might be a little bit, out of left field, but you'll see why they're important. We will use ultimately the set A equals x in AB such that f of x is less than 0. So my claim is going to be that the c value that we can find using our argument where f of c is equal to 0 is actually the supremum of this set. So imagine that I had a graph. It could be, that our function crosses the x-axis multiple times. So I'm going to redraw this picture. So I could have a function that goes up and then back down and then goes back up again. The point is that there eventually has to be a last time that our function crosses the x-axis. And the argument that we're going to use is that last time is right here, and that value, the x value, is the supremum of the set A that I just wrote down. So the set A, notice that I'm talking about a collection of x values such that when you plug them in, the function is negative. And so what that means, if I look at my graph, A is going to be, capital A is going to be the set that I'm highlighting in blue. It's all of these x values such that the piece of the graph that I get lies below the x-axis. So to be clear, A is a collection of inputs. They are inputs such that when you plug them in, you get something below the x-axis. So what we're going to show is that, so we will show that f of c equals 0 when c is the sup of A. And we're going to do this by contradiction. So what that means is we're going to assume toward a contradiction that f of c is not equal to 0. And the key to getting our contradictions is going to come from what happens when you just look at the definition of a supremum. What we're going to see is that our argument is going to break down into two cases. And one of the cases will use the fact that C is an upper bound for A to get a contradiction. And the other case is going to use the fact that C is the least upper bound. And we're going to get a contradiction to that statement. So here is our sketch of our proof. So we're going to assume toward a contradiction that f of c is not equal to 0. That means that there are two cases. Either f of c is greater than 0 or f of c is less than 0. So let's take a look at our first case when our function value is positive. So f of c is greater than 0. So I'm going to draw a picture of this case. And we're going to take a look at what goes wrong. So again, our assumption is that A is the one that evaluates to a negative function value. And B is the one that evaluates to a positive function value. And what we are assuming in this case is that the C value that we are finding, which is supposed to be the supremum of the set capital A, is going to be positive. So that's what we've assumed. So we know that our function is continuous, which means that if I put any epsilon band, for example, around f of c, because I know it's continuous at c, so say this is my epsilon band, then what should happen is I should get a delta value, a delta neighborhood, such that over that delta neighborhood, all values of my function, any x that I plug in, should give me a piece of the graph that lies, up here somewhere over this, inside our epsilon band. So remember, I'm supposed to be able to say that for any x I pick in here, here I'll put it to the left, for any x value that I select, that x value should come up and be here inside my neighborhood. So the idea that we want to use here in our argument is we want to think about what this has to do, like why does it contradict the definition of supremum? And to see why that's true, we want to choose an epsilon neighborhood that lies entirely above the x-axis, so that all outputs of my function on this delta neighborhood are going to have to be positive numbers. That is actually going to be a contradiction to the fact that C is the least upper bound, because our argument is going to show that C minus delta, for example, is also an upper bound for A. So, idea. We want to choose epsilon greater than 0 such that the epsilon of f of C lies entirely above the x-axis. That tells us that every single x value we select from the delta neighborhood is going to have to be a positive function value when you plug it in. And furthermore, that means that any x in the delta neighborhood is not in the set capital A. Because remember, capital A only contains negative function outputs, or x's that output to negative numbers. So here, what's our contradiction? It's going to be that C minus delta appears to be an upper bound for A that is smaller than C. So that's what we're going to have to try to show. So if you remember how soups work, we could use this lemma to try to see what was going on. So we had, like, if this was our soup of A, then if I made soup A any smaller, usually we were subtracting an epsilon from here, but I could call that soup A minus delta. So in that way, I'm kind of referring to this number as C, this number as C minus delta. I'm supposed to be able to get an x value in this neighborhood such that x is in A. Because remember, this number C minus delta is not an upper bound for A because it's smaller. It's not allowed to be. The soup is the least upper bound. However, if you notice, that x is in the delta neighborhood. And because that x is in the delta neighborhood, it has to, f of x has to end up in the epsilon band, which is a positive value. So how am I going to get x to be in A? Because remember, the x's in A have to evaluate to be negative numbers. So I'm going to write out the full proof of this. So this is the proof of case 1. So remember, we are assuming toward a contradiction. That f of C is a positive number. And since f is continuous on AB, for epsilon equal to f of C, which is a positive number, or any 0 less than epsilon less than or equal to f of C, it should be true that we have a delta neighborhood corresponding to it. The reason why I'm picking any epsilon between 0 and f of C is because I want to construct an epsilon neighborhood that only consists of positive function values. And in that way, none of the x's in the delta neighborhood can belong to the set capital A. So I know by definition of continuity, there has to be this delta neighborhood such that for all x in the delta neighborhood, f of x is in the epsilon neighborhood of f of c. By choice, v epsilon of f of c lies entirely above the x-axis. So that tells me that for all x in v delta of c, f of x, because it's in the epsilon band, has to be bigger than 0. Therefore, x is not an element of capital A. Now we need to show why this contradicts lemma 1.3.8, which is supposed to show us that sup A minus delta can't be an upper bound for A because it's a number smaller than the supremum. But we'll get a contradiction because we know that no such x value is going to exist between sup A minus delta and sup A. So by lemma 1.3.8, since c minus delta is not an upper bound for A, there must exist an x in A such that c minus delta is less than x, which is ultimately less than or equal to c, because c is an upper bound for any x in my set. This x in A is in v delta of c. So on the one hand, we're saying that x is in A, which means f of x has to be less than 0 by definition of the set capital A. And on the other hand, we have already shown that any x in our delta neighborhood evaluates to be positive when you plug it into the function, and that's a contradiction. So here we have a contradiction. We said any x in v delta of c is such that x is not in A. We just got done saying we're supposed to have an x that is in A, but we already said that's not possible. So therefore, I know that if I look at f of c greater than 0, that statement is false. So we need to now consider the case where f of c is less than 0. Because remember, we assumed f of c was not 0. We've shown it can't be positive either. Now we need to show that it can't be negative. So now we're going to look at case 2. And we're going to assume that f of c is less than 0. And again, we're trying to arrive at a contradiction. Now, our first case, the contradiction was to the fact that the supremum of A is the least upper bound. So the expected contradiction that we might have in this case is perhaps that c equals sup A is not even an upper bound at all for A. And remember, when you're not an upper bound, that means that perhaps we're going to find that there is an x that is in A, but that x is larger than c. That's how I would show that c is not an upper bound. I'd find an element in the set that's bigger than c. So in our previous case, we said the key was to construct an epsilon neighborhood that lied entirely above the x-axis because we were dealing with a function value that was always positive at c. Now we're going to do a similar argument, but we're going to guarantee that our epsilon neighborhood that we select lies entirely below the x-axis. And the reason why we are doing this is because, again, due to continuity, we should be able to get, for this epsilon neighborhood, we should be able to get a delta neighborhood. So here we've got c plus delta and c minus delta. And no matter what x value I plug in from that location, I'm supposed to get a piece of the graph that stays inside this neighborhood. And so what that really means is that any x value that I plug in from inside this delta neighborhood, I should get a corresponding f of x value that is in my epsilon neighborhood, but in particular, that f of x value has to be less than 0. And if it's less than 0, that's telling me I just found an x that's bigger than c, but x is in my set A, and that's where I'm going to get my contradiction. So again, the key here is to specify an epsilon neighborhood that only contains negative numbers. So our proof is just going to be choose epsilon such that v epsilon of f of c lies entirely below the x-axis. So for example, we can let epsilon just be the distance of f of c to 0, which is the absolute value of f of c. Or we could use any other 0 less than epsilon less than or equal to absolute value of f of c. And then since f is continuous at c, there has to be a delta neighborhood such that for all x in v delta of c, f of x is in v epsilon of f of c. By construction, this means that f of x is less than 0. Because remember, we chose an epsilon neighborhood that only contained negative numbers. So by construction, f of x in v epsilon of f of c implies f of x is less than 0. Thus, by definition, for all x in v delta of c, f of x is going to be negative. So in particular, it's better for me to say here, x has to also be in A. So what we've really shown is that the entire delta neighborhood of C is contained inside A. So then the reason why this is a contradiction is the fact that any x in V delta of C such that x is greater than C is an element of A. Therefore, C is not an upper bound. Because we have found a number larger than the supremum that's in the set. So this is a contradiction because C is supposed to be the sup of A. So what we see here is that f of C less than 0 is also false. And so overall, because we have shown that f of C can't be positive and f of C can't be negative, f of C has to be equal to 0. Now there's one question that we haven't technically addressed here, and that's why does sup A even exist? So our whole argument relied on being able to say that we had this supremum, and we never actually used the axiom of completeness to say it existed. So remember what our set A was. It was the set of all of our x values in the closed interval AB such that f of x was negative. If I want this to be, if I want the sup to exist, I need this set to be non-empty, and I also need it to be bounded above. So I need to think about what x value do I definitely know is in this set capital A. In other words, when I plug it in, f of that x value is less than 0. Well, we know that A is in A, because that's our assumption. We assumed that f of A was less than 0 and f of B was greater than 0. So we know A is in A because we assumed f of A was less than 0. So therefore, A is non-empty. The other thing is I need to figure out a number that bounds my set above. But notice the set A, by construction, is just a subset of x values in this closed and bounded interval AB. So because A is a subset of a bounded interval, it has to be bounded. In particular, this set is bounded above by B. So therefore, by the AOC, sup A exists. So we did actually have this C value that we could be arguing with. One of the applications of the intermediate value theorem is that it's very useful for proving that two functions actually intersect at some point x. Right now, the graph of the IVT and the statement of it is saying that the function, like if you have a function and then a line, y equals L, you have to intersect at some point over that interval. But we can actually extend that to say that two functions have to intersect. One of them doesn't necessarily have to be a line, as long as those two functions are continuous and you can show that the hypotheses of your intermediate value theorem statement are met. So the IVT is useful for proving f of x equals g of x for some x when f and g are continuous. Well, and when they actually intersect. So there is one more thing, we have to check the hypotheses. Remember that the IVT is saying when you get a number capital L that lies between two function values and you're continuous over that interval, then you know that there's a place where you achieve the value L. So we need to figure out what function we want to use here. We know what to do to show that f of x is equal to a constant L. But here I'm trying to show that f of x equals g of x at the same time, the same x value. I don't want to just go and say, okay, set f of x equal to L and set g of x equal to L, because it could be that f of x1 is L and f of x2 is L, where x1 is not equal to x2. We need the same x to solve the equation. So the way we do this is we just let h of x be the function f of x minus g of x. You put everything on one side. Think about when you want to solve a function, like for intersection points. Usually the first thing you do if you're doing it by hand is you put everything on one side and then you try to factor and figure out when the function is equal to 0. If you're going to use this shifted function, then we need to make sure that it's continuous, because we can't use the IVT without continuity. So we have to ask the question, well, why should h be a continuous function? Well, it's the difference of continuous functions. So h is continuous by the ACT since it is the difference of continuous functions. To show h of x equals 0 for some c in AB, we need to find an A such that h of A is less than 0 and a B such that h of B is greater than 0. If we can do that, then L equals 0 is playing, like 0 is playing the role of L in our statement of the IVT, and the IVT would say that there has to exist some C in between A and B. Without loss of generality, I'm going to assume that A is less than B here. It could be the other way around. But it says there exists a C in here such that h of C is equal to 0. And so what that really means, using the definition of h of C, is that f minus g of C is equal to 0. And that implies f of C equals g of C, and we found our value. You might practice, well, actually there's going to be a practice problem that I post for you where you try to prove that f of x is equal to x for some x, given certain domain restrictions. You want to think of this x value as being your function g. I'm not saying that f of x is the function y equals x. I'm saying that f of x intersects the function y equals x at some point. So if I were to graph y equals x on my line, I'm making the claim that somewhere over my interval, I should have an intersection between y equals x and y equals f of x. So I'm not saying, this is not the typical function definition here where you say let f of x equal x, and then it's the graph y equals x. I'm saying there exists an x. I'm not saying for all x, these are equal. So you'll have a chance to try to use the IVT to prove that in the homework. In the practice homework, because it's not going to be graded. But that's it for this section.